Alright, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. I don't think it's over here anymore. Hit the bell if you want notifications for the series. Otherwise, please subscribe. What we're doing is Linear Algebra 1. Chapter 5 is Linear Transformations. 5.1 is going to be Linear Transformations and their basic properties. And this lecture specifically, what we're going to do is define a linear transformation between two arbitrary vector spaces. For us, it'll be Rn and Rm usually. And then we're going to talk about the properties of being one-to-one, onto, and then if you have these two properties, it's the nice ones that we want is bijective transformations. Let's get to it. All right, definition. What is a linear transformation? Let U and V be vector spaces. In general, U and V are going to be just the vector space Rn and Rm. Quite often, we're going to also call it what we call an operator if it's U and V are the same set. But for now, make them abstract, arbitrary vector spaces. A transformation T, which goes from U, this vector space U, into the vector space V, is a correspondence or a rule that assigns to every vector X in U a unique element Y in V. We'll also write, this is going to be our notation in general, T of X equals Y, just like we do in function theory, but this is doing it in higher dimensions instead of from R to R. Furthermore, we call U the domain of the transformation T, and V the codomain of the transformation T. And pictorially, just like in calculus, the way that we can view this is if you have some vector space which is a set U, and then we have another vector space which is a set V, then what we're doing is we're moving points from U, we're moving them around in V. If it's the same set, we're moving points around in that space. But what we do is we take a vector or an element X in this one, where are we going to send it to T of X, which is we're going to call Y for simplicity because it's just a new point in this new vector space V. Let's do some properties of this now. All right, our next definition is the major properties of a transformation. Let T from U to V be a transformation. Then T is one-to-one or injective if distinct vectors x1 not equal x2 have distinct images, so T of x1 is not equal to T of x2. This is not actually how we show it in general, whether it's a function from calculus or these transformations we're going to do now in linear algebra. So if I negate these statements, we can have the contrapositive, which is going to tell us that if we have that the images are the same, this has to imply that the points are the same in the domain originally. The other property we have is T is called onto or surjective if every point Y in the codomain, there has to exist at least one X in the domain such that T of X is equal to Y. There's an alternate way of phrasing what onto is that the entire image under U has to be equal to V, but we'll show you a way of calculating this for some basic transformations so we can get around this one. This one's much more nasty than one-to-one the first time you see this. And then the nice property that we want is, in fact, we want T to be a bijective operator or transformation. Operator is a transformation which goes from the same space to the same space. So it's bijective if it is one-to-one and onto. So we want it to have these two nice properties. If it does, we call it a bijection or a one-to-one correspondence. And it turns out a one-to-one correspondence is the ones which are invertible. So the inverse of these functions will exist if and only if it's bijective. Let's do an example. For an example 1, T of X is sine X, or Y equals sine X, is a transformation from R to R. So we have this function sine, which is going from R to R. It turns out this function is neither one-to-one nor onto, because we're going to have, for instance, so if we're going to look at one-to-one, first of all, 1-1 is my lazy way of saying that. So 1-1, one-to-one, is it going to be one-to-one? Well, all I have to do is, what we're trying to say is, if sine of x1 equals sine of x2, this has to imply that equals x2. That would be one-to-one, but we're not going to have this. Why? All we have to do in this case is cook up a couple of points where we have the same image but they're not equal to the same value. So in this case, I know that, for instance, sine of pi over 2 is equal to 1, which is also equal to sine of 5 pi over 2, but that does not imply that pi over 2 is equal to 5 pi over 2. Otherwise, I would say 1 equals 5, and that's clearly a contradiction. So this is not one-to-one. It's also not onto because we know that, so for onto, we're going to have that negative 1 is less than or equal to sine x is less than or equal to 1. It's stuck between minus 1 and 1. It's a wave that's between amplitude minus 1 and 1. So take, for instance, any point in the real numbers. We have to find somebody who has its image, but we won't. So take y equal 2, say. We don't have to get super fancy. Then there is no x in R with sine of x equal 2. So not 1 or onto. Not onto either. So this function is not one-to-one. It's not onto, therefore it's definitely not a bijection, and in particular it's a wave. It's not going to be linear either, but we'll get into what a linear operator or a linear transformation is in a second. First of all, we're just dealing with transformations in higher dimensions possibly, but either way, these are the two most important properties, one-to-one and onto. Let's do another one. All right, example 2, we have a transformation going from R2 to R2 now, and t takes a vector x1, x2 and sends it to this vector, x1 minus 3x2, negative x1 plus 4x2. First of all, I want to know if this is one-to-one. One way to do this is ad hoc, so what we want is if t of x equals t of y, say, what we want to show is x equals y. So how are we going to get that? That would be by definition that this is t of x. So that would say that x1 minus 3x2 negative x1 plus 4x2 has to equal y1 minus 3y2 negative y1 plus 4y2. And now we use the condition when our vectors equal to each other. These two vectors are equal if and only if both of their coordinates are equal. So now that tells me that I'm going to get this. I'll have x1 minus 3x2 equals y1 minus 3y2, and we're going to have negative, or I'll write it below it because I'll do a clever ad hoc trick, negative x1 plus 4x2 equals negative y1 plus 4y2. If I add these two equations, what do we get? Cancel, 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 cancel. 4 plus negative, this will say that x2 equals y2. So we did get already that the first coordinate was equal of these guys. And since that's true, putting that into, say, we have equation 1 and equation 2. If I put that into equation 1, the fact that x2 equals y2, this says x1 minus 3x2 equals y1 minus 3y2 is equal to x2. So I can put that in there. I know I'm doing it just a second that I can cancel these guys, and what does that say? That says x1 is also equal to y1. So that says that x, which equals x1, y, or x2, is equal to y1, y2, which is equal to y. So if their images were equal, I showed that those two vectors are equal, and this says one-to-one. So yes, it's one-to-one. Now how do I show onto? This will be a little bit nastier trick, but let's clean up the board and then I'll show you. For onto, what I need is for any y, which we're going to call, say, AB for simplicity, in R2, which is our codomain, we need at least some x, which we can write as x1, x2, such that t of x is equal to y. That's what we're looking for. If I can do that for everybody, then we are going to be onto. The way I can phrase that is I can now look at what this is going to be. What is t of x1, x2, which is actually going to equal x1 minus 3x2 negative x1 plus 4x2. That has to equal AB. Now I can augment a matrix and find out whether I'm going to have this. Can I find at least one x1 and x2 such that they'll equal A and B every time? What we're going to get from this is a linear system. I have now x1 minus 3x2 has to equal A, and negative x1 plus 4x2 has to equal B. I augment the matrix. I'm going to get 1 minus 1, negative 3, 4 equals AB. I'm going to add these to get 1, negative 3A. I get 0, I get 1, I get A plus B. And so what does that tell me? That tells me that I have it, this is REF, I have a unique solution. What is it specifically? This says x2 is equal to a plus b, and it says that x1 will equal a minus or plus 3 times x2, which is a plus b. So that says x1 will equal 4a plus 3b. These two coordinates tell me that every time I do that, I will exactly get the vector y. So this says I do have at least one vector x1, x2, such that when I take the image of these guys, I will get y. I'll do it in a second. So this says that we definitely have yes, it is onto. Turns out if you're in the same dimension, you're one-to-one, if and only if you're onto, if and only if you're bijective. But just a second. So actually seeing that, that gave us the coordinates. Let's use that now. What that tells me is if I did x1 equals, what was it, 4a plus 3b, and x2 is a plus b, then what is t of x1, x2? This is equal to t of, I didn't put the extra brackets because I'm lazy, 4a plus 3b, a plus b. Where does that send it? It tells me it has it send it to, takes the first coordinate and puts it there. So 4a plus 3b minus 3 times x2, which is this guy, a plus b. And then in the next one, I get negative 4a plus 3b plus 4 times a plus b. And that gives me what? Equals 4a minus 3b is a. And then 3b minus 3b is 0. And negative 4a and 4a is 0. And negative 3b plus 4b is b. So t of x is equal to y, explicitly, onto, definitely. All right, we're on the home stretch. Composition of transformations now. When we have more than one, notice that the codomain of t has to equal the domain of s, v. But if we have a transformation t going from u to v, and then we have a transformation s going from v to w, where we have 3 vector spaces, hopefully they're the same in most cases, then the composition of t and s, or the way we say this is s following t, just like in calculus or when we do function theory. The composition of t and s is the transformation defined by s following t is s of t of x. Essentially, the picture is extremely useful. I pick a point u, or x in u, I pick a point x inside u. Then what happens is t moves it to t of u, which we're going to call y possibly. And then this is just a point in v now, and we're going to pick up that point, and what are we going to do? We're going to evaluate it at s, so that should be s of t of x, which we could call w. But this is just moving the point x in u to the point s of t of x in w. Therefore, we get an alternate way of viewing this, cutting out the middleman essentially. R is s following t. And this is how we define it for every point. We're not going to use it too much in this course. Basically, what I need it for is to show that we have, what I'm going to do next is define what the identity operator or transformation is, and then how to find the inverse transformation of a transformation, if and only if we'll get conditions for this. This is the one messing with everything around there. This is Alice. She's super friendly, and she wants to know what the heck is going on. So we're doing transformations and composition of transformations. Let's do it. And then we're going to do identity transformation for the transformation I from u to u. All right, so the last two things we need to define invertible transformation, we need the definition of identity operator or transformation. Transformation I from u to u, such that I of x equals x for all x in u, is called the identity transformation or identity operator. We call a transformation an operator if it goes from the same space to the same space. We call a transformation t from u to v invertible, and we'll call S the inverse of this, just like in matrices and everything else. We call it invertible if there's some transformation from v to u, such that the composition of S and t is always the identity operator, and the composition of t following S is also the identity operator on v. If we have this, we call T invertible. And now what we're going to do, the last thing we're going to do, right, Alice, is give us a necessary and sufficient condition for when an operator is in fact invertible. All right, we're on the home stretch. Good thing the battery in my camera's dying anyways, and I have to switch to the new one. Don't worry about it. Theorem. If T is a transformation from U to V, oh, what do you got there, kitty? Right, no, she stopped doing that. She's got the lens cap for the camera also. Theorem, let T be a transformation from U to V, where U and V are vector spaces. Then we say T is invertible if and only if T is one-to-one and onto, i.e. T is invertible if and only if it's a bijection. So this gives us a necessary and sufficient condition. If it's bijective, then the inverse exists. If the inverse exists, then it must be bijective. And once we've done that, now we're not going to call it S anymore. What we're going to do is we will denote the inverse of T by T minus 1, as we did with everything else. Just like we did for matrices, A inverse and a number inverse. We're always going to use this minus 1, and now we have T inverse. It turns out linear transformations are matrices, and we'll make this connection next time. So it turns out all this work that we've done, we still haven't defined what a linear transformation is. Next time what we'll do is, of all of the transformations we can have between vector spaces, one of the specific useful ones that we want, or the ones that we're going to be interested in, are linear transformations. Next time what we'll do is we'll make a link between linear transformations and matrices. Every matrix can induce a linear transformation, and every linear transformation has a standard matrix, so we can view linear transformations as multiplying by matrices. That'll be next time. Please subscribe right here. I'll see you then.